Okay, good afternoon. Thanks for your patience. I'm sorry because there is the keyboard that doesn't recognize the password. I hope that the recording works. So let me now share the screen and let me see if okay. I get my website. Here we are. And let me share the screen. Share screen. Not now. Okay. Okay, how are you doing? Everything is fine? Perfect. So, this is our last meeting, but of course I remain at your disposal for in the future if you have any curiosity, any need for clarification. So, let me jump to our discussion on climate change impact on health, and I open the PowerPoint here. So, here we are.
I thought we had another question.
Say again?
I thought we had another question.
With Professor Topolongo. I think. Yeah, you are. I think you still have also classes in January. But with Professor Topolongo, I'm not sure who is teaching. But not. It shouldn't be with me because I had to teach 12 hours. So this is the last one. Okay. So we were. Sorry. We were discussing climate change impact on health, and a brief summary. First, we introduced an analytical method, an analytical approach in order to estimate the risk induced by climate change on health, and we have seen that to estimate this risk, we can express it as the product of hazard, vulnerability, and exposure. Hazard is the part that is mainly influenced by climate change. Also, vulnerability can be influenced by climate change, but to a minor extent. And yeah, 1 second. Okay. Hazard is mainly influenced by climate change, I was saying, and then we discussed how to estimate the three of them. And one important thing that we mentioned last time is that the estimation of, in particular, vulnerability and exposure, but also hazard, can be carried out through health determinants. Health determinants are indicators of climate change impact on the human health. These health determinants, in a way, are translators, are connections between climate change and our personal health at the individual level, but also at the community level. And these indicators can be, as we said, climatic variables, can be societal variables, economic variables, because, for instance, they may be related to the public debt of the state, they may be related to the state of the healthcare system. And this is probably the part that is more innovative, more in the domain of science. They can be combined. In a way, we can combine, for instance, a climate change indicator with another determinant, perhaps of social nature, and to express through, for instance, a multivariate probability distribution, the chance of occurrence of critical values of both. So we may, for instance, map climate change through a proper climate variable, like extreme rainfall. We can make a map. We can make a map of the status of the healthcare system, or we can make a map of another indicator like water security. And then we put the two layers one above the other, and we identify where there can be the superimposition of critical states, because as I mentioned to you, very often catastrophic events are determined by the superimposition of causes, superimposition of critical states. So there might be a situation that already the baseline is critical. And then with the occurrence of climate change, this critical situation explodes. So we started discussing health indicators, and I move forward in the presentation. And we have seen these diagrams which relate climate change mitigation and adaptation measures to the final result of diseases, of health status. I think these diagrams are particularly important because you can get with them not just the connections, but what is important is the list of the sectors, the list of the measured categories for climate change mitigation and adaptation, the possible list of health determinants, and the list of the health outcomes. And then we started discussing the indicators. And you may remember that I finished last lecture by showing to you this slide, which shows for the extension of China, the number of hours of physical activities, hours per day, that is lost due to the occurrence of heat waves. And this is just an example. And you see that there is a trend. Of course, there is an increase of temperature, and this means that people cannot make physical exercise anymore. In most of the cases, these connections between climate variables, climate change, health determinants, and health status are very obvious at the qualitative level. At the qualitative level, it is very obvious what I will also tell you today, like an increase of temperature means an increased number of days without temperature, which means in this case less physical activity. It's very obvious. What is less obvious is to model this relationship, these links, in order to get a quantitative estimation. This is less obvious, and this is where the research is still very active today. I will show you some examples just to get to you a perspective of the problem. And then I closed with this graph. I realized that I didn't explain it well, so I just want to show it to you again. This graph refers to several regions of China. And for any region, it shows health indicators, like, for instance, the first one in the legend on the left is heat wave-related mortality. Let me just check if you can read it. Yeah, it's not easy, but it's the upper one, heat wave-related mortality. And then you see for any region, in the color, in this case is orange, you see two indications. There is a bar with conic shape, which illustrates, says, the ratio of reported values of the indicator for the last year, is 2022, with respect to the baseline in 2016. So if you see the circle, a circle, for instance, here indicating 10 for this region, it means that the ratio between the reported value of the health indicator in 2022 was like 7 times higher for this one with respect to the baseline, which means an increase of the health risk. And this is for the conic shape, different colors reported in the legend. And then there are the circles. The circles refer to the population with age that is above 65. So you get this indication for these health determinants for all regions of China. And this is something that is reported by I think it is from this publication, Kai et others, which uses indicators that are taken by the Lancet Countdown, which is the report that I mentioned to you. The Lancet Countdown is a report, and I want to show you the link, is a report that discusses several health indicators and their values. So let me just get it. It's here. This is just a figure. This is a figure which shows the progress of heat wave days at the global level with three references: the global mean over the land. So the heat wave days are computed over the land, and then there is the curve which shows the same value for infants, and the curve showing the same value for older than 65. So basically, they look at the population. They look at the population that is exposed to heat wave days, and for different ages, they make these curves which show to you the progress along time. And this is a useful reference for you, because you can see, based on the health indicator they selected, how they progressed in the past, in this case, 30 years. And let me just get the link of the Lancet Countdown. Just 1 second. It should be something here. And here on the webpage of the Lancet Countdown, yeah, you don't see it. Okay, sorry. I just need to. Correct. So you didn't see also the figure first, and then you didn't see this one. Okay. The reason is that when I am in presentation mode, I'm sorry, but I'm starting I started last time to understand how this works. When I am in presentation mode, it doesn't show the other pages. So now I am here, and here now you should see. Perfect. So this is the Lancet Countdown, and you see it's a countdown on health and climate change. Why? Lancet is the famous journal publishing articles on medicine. You know it better than me. And the countdown, why? Because they indeed track the progress of these health indicators. And here, if you look at the links, here there is the report. And just let's give it the time to download it. And you see here the 2023. Last time I explored it, it was 2022, and I took the figures from the 2022 report. Now they already published the 2023, and is the report on health and climate change. And here you see there should be somewhere the indicators, evolving regional inequity. Okay, let me see PDF. Because this is the fact. Here we are, I think. And okay. Okay, here there are the links for the indicators. It's the first time that I explored the 2023 one. I don't want to spend more time on it. Just to give you the reference and take into account that this is important for both getting an idea of the indicators and getting the progress of these indicators a long time. Okay, now let me just go back here.
What the circles and
Yeah. Let me just get it in the website, because so you see, because there is a description in the website. And let me just go here. Good. And okay, here there is a figure. Let me open it in new tab. But first, let me just look at if you see the caption, the values of the conic bars and dots in each provincial figure represent the ratio of the latest year values to historical baseline values. And this is taken from a paper of 2022. Let me now zoom it. And let's take, for instance, this one. Now should be more visible. The legend. Okay, let's look here. The value 5 means that the ratio between the value in the latest report and the baseline indicator is 5. So if you look at this conic bar, for instance, for yellow is heat-related physical activity safe hours lost. It reaches the value of 5. It means that they lost 5 times more physical activity in 2022, because this is the first 2022, with respect to 2016. And this is for the bars.
2016.
Yeah, 2016 is the value of the indicator in 2016. So it means that in 7 years, they lost 5 times more, this is the ratio, hours of physical activity. Of course, you should look at the report if you want the number. If you want the number, you should look at the report. And the bars are for all age group, while the points, you see that there is a point here. The point is for the age greater than 65. And you see that the loss was lower. But the reason is that at the age of 65, they don't make a lot of physical activity. So the loss was lower. There is also to say, I don't know that, but you know that elder people may suffer less heat waves or the hot weather with respect to young people, because they may be more suffering these thermal stresses for medical reasons. But I'm not sure what is the reason why indeed here the loss is less than that. We should look at the reference, which is open access linked in the web page.
For the normal colorful bars, like for all age groups, including over 65?
Yes, all age group, all age. And then when you look at over 65, in this case is lower. There are some indicators where it's higher. Of course, it depends on the indicator that you use. Okay.
And they repeat it every 7.
No, it's repeated. The Lancet Countdown provides the report on the value of indicators for several regions in the world every year. And in this case, this graph is prepared by a scientific publication. It's presented in a scientific publication. I didn't check whether this graph is also available in the Countdown. I would say no. I think that they got the values from the Countdown in 2016, because the Countdown is published since 2015. So they got the first value of the indicator from the Countdown and then prepared this graph for the regions of China. Okay, now let me go back to presentations. And it was here, good. Okay, very good. Now, these indicators, which are presented in the Lancet Countdown, should satisfy some requirements. And these are the requirements that I very quickly introduced to you last time. And the requirements are listed here. Representativeness means that the health indicator should track an aspect of both climate change and health. And if it is a climatic variable, it should be made explicit, the connection between the climatic variable and health. And you see, particularly focusing on the relationship between the two. And this relationship, as I said, is a subject of ongoing research. And what is interesting, the research is particularly interested in exploring the situation that may lead to an amplification of the impact, where even a small change in climate may imply a big change in health conditions. This is a very critical question. And it's not easy to provide a reply, because actually we don't have many opportunities of making experiments. We can refer to other contexts, to experiences made in other situations where the weather is warmer. But actually, the implication on the health also depends very much on the local conditions. Relevance, a health indicator should be clear and understandable to a broad range of audiences, and should be indeed relevant. Robustness means that once estimated, the indicator provides an indication that is solid. We use the term robust to identify models or variables which may be not very accurate. They may be estimated with not a very high accuracy, but with not relevant mistakes. So when we say a car is robust, it means that the car may be not so performing, but I can trust it because it's it doesn't fail. And robustness means precisely that. Reproducibility, which is a basic requirement for science today and also medicine. When you make experiments, and when you present scientific results, they should be reproducible, and timeliness, which means that the health indicator should be suitable to be calculated regularly.
I didn't understand your words. How can we trust it?
Because there are situations in which, when you get an estimate, you are not really interested in very fine accuracy. You are interested in the immunity from big mistakes. And this means robust. A statistical model is robust when parameter estimation is not very precise. It doesn't lead to a very precise result. What does this mean? It means that you have an uncertainty band that is not very thin. On the other hand, for the purpose that is used, is never misleading.
But how can it not be misleading?
Because you may have a method that is precise, very accurate 90% of the time, but the 10% of the time that is not accurate may be deadly wrong. You may have another method that is never deadly wrong, but it doesn't have the same accuracy that the previous one had for the 90% of the times.
So it's within a certain confidence.
Yes. So when you make the mistake, basically, when you look at the mistakes made in destination, the probability distribution of destination error, the probability distribution is not one-tailed, which means that the average may be 20% error, but you never reach 95% or 200% error. Instead, you may have probability distributions where you have on average a very small error, like 1%, but with a very low chance, you may have an error of 1,000%. This is not robust. It means that it's not robust. Is this clear, or would you like I make a sketch of the blackboard? It's
Pretty much, are you going to draw the probability distribution?
yeah, no problem. And okay, let me see if it's already should work. Okay, so let's okay, let me check. Check if it works. Okay, now it works. Okay, probability distribution. So let's draw it in terms of probability density. Okay, so you may have, and here the variable, the random variable is like a percentage error. Percentage error of something. Let's suppose that we refer to an health indicator, and when I estimate it, I get a percentage error. Okay, so you may get a probability distribution that is like this. I'm sorry, I don't like this. Here. You may get a probability distribution of the percentage error like this. And this may be something like 50%, or let's say 10. Okay, let's put here 10%. And here it's like 5%. And here it's like 50. Okay, this is
so low. Quite low.
Low, you mean in terms of percentage? Yeah, maybe, but you can change it. It's just an example. Okay, so number of heat waves. Let's suppose that here you have a range of error that can vary between 5% and 15%, and the average is more or less 10. Okay. Now let me see if I can change the color.
You can't.
I think so.
You can change it.
Yeah, okay, but I think this is fine. Let's suppose that you have another, and this is 0, okay, 0%. Let's suppose that you have another distribution, another estimation method that works in this way. So you have a spike here, and then something like that. So it means that you have, on average, an estimation error that is much lower. Keep in mind that the area below the curve should be the same. It's 1. Okay, probability distribution, when you get the integral, the area below the curve is 1. If you don't understand what I'm saying, just stop me. And with a reduced chance, you may have a much larger error, because this is the end of the previous distribution, is about 17%, and this distribution is long tail. Okay, so it means that with very low probability, you may get an error of 200%. So this is more robust.
Which one? Black one?
Black one. Because you get a larger percentage error, but never a very high one. This one is less robust. It gives more accuracy, you see, on average, but you may get a big mistake. So if you look at the average error, you would say this is more accurate, because on average is more precise. So there are some cases, and particularly when you deal with natural hazards, you don't want prediction of floods to be completely erroneous on both sides, because if you get false alarms, then the public doesn't trust the alarm anymore. And if you don't issue a real alarm, then it's a big problem. You prefer a robust method, which when you issue an alarm, people know that, okay, it may not happen, but in general, it's reliable.
But in the red one, the high percentage errors probability is so low.
Because you may have some estimation methods, some models that in some cases are very wrong.
So I thought red would be.
Yeah, the red one could last forever. There are some distributions. This distribution with a very long tail are called long-tail distributions. It means that, and this is particularly, you may refer, for instance, if you forget, if you change the variable here, like flood flows. So the river flow when a flood occurs, then you are much more concerned by the red distribution, because it has a long tail. It means that with very low chance, you may get a big flood. This distribution is more reassuring. It means that I am exposed to floods, the black ones. I am exposed to floods, but on the other hand, they are floods of controllable, under control magnitude.
So we should prefer robustness.
It depends on the application that you deal with. When we make scientific research, sometimes we look for models that are accurate, because we want to test the models and to test the theory. So we may accept the fact that these models fail sometimes for some experiments. But usually we want, for scientific purposes, we want the perfection. So we try to identify the best model, even if it's a model that is applicable only in a very controlled situation. Because, I mean, the model that is not robust usually needs a lot of information. It's a very complex model. When you increase the complexity of a model, usually you lose in robustness. And I think this may apply also to some cases in medicine, but I can't find an example. And and very large complexity means that you need a lot of information. You can think of a therapy that is very complicated and very risky, and you need a strict monitoring of the condition of the patient. And if you can't monitor the condition of the patient regularly, you may prefer a therapy that is more robust, maybe not the best one, but the best one if you don't have the opportunity to control the patient. I would say in this case that the therapy is more robust, but I'm not sure if it is used in medicine, even if the fact that it's used here I think, is significant. And so for models, when you have a controlled situation like a laboratory experiment, you can increase complexity because you have a lot of information. But when you go to the real world and you don't have a lot of information there, you may prefer a model that runs well even in the absence of the information. Usually it's a simpler model, it's less accurate, but it minimizes the probability of a big failure. This is the probability of a big failure, you see. Okay.
So even though the probability of big
because if you look at the black curve, it is, you don't get a big failure because the probability distribution is defined from 5% to 15%. So you don't get a big failure.
So we don't have the estimate.
No, I mean, I have drawn it in without the long tail on purpose because you exclude the big failure. Okay, this is an example of an indicator which is presented by the Lancet Countdown. Exposure to warming. So basically, they found that from 2000 to 2021, population were exposed to an average increase in summer temperature, 2 times higher than the global mean. And therefore, they define this indicator, which is computed by computing the number of heat of very warm days. This is just an example, but if you browse the countdown, you see a lot of them. I don't think it is really important for you that you get a... Sorry, I forgot to change the screen. Should be just 1 second. Okay. So basically, this is 1 second, exposure to warming. I mean, I don't think it's important for you that you go to browse this Lancet Countdown because the list of the indicators is just a mere list, and the indicators are many, as you will see. There are other organizations that proposed other health indicators. What is important is that you get the concept of the health indicator and you get what are the open questions, which is the chiffering, estimating them, and deciphering the interaction between the indicator and climate. Okay, now, so we already discussed this, what are the climatic states that are considered to be most influential? Of course, we may identify several climatic variables to adopt as health indicators, but if we want to converge, if you want to make a selection to identify the most significant, these are the events that are considered to be more effective on human health. So extreme rainfall, droughts, and so an indicator of drought could be interesting. And the indicator of drought could be, for instance, the water supply deficit. So you look at the water supply system, you look at the flow, the water flow that is delivered by the water supply system, and you define the deficit as the volume of water per unit time that cannot be delivered. So the deficit with respect to the water demand, and this is a big influence on health for obvious reasons. And then heat waves and windstorms. To be clear with you, these are events that are in principle not dependent on climate change. I mean, even without climate change, in the normal climate, we may experience extreme rainfall, droughts, heat waves, and windstorms. The history of humanity is full of events of this type. And of course, there is the question if climate change is increasing, and we believe that climate change is increasing the frequency of these events. But independently of climate change, what is interesting for you is to know the events, the climatic events that, climate change or not, may have an impact on the human health. And we will see also focus on the diseases, on the specific diseases. So, actually, why I'm saying this? Because it is debatable whether climate change has worsened significantly the human health, and especially if you focus on single consequences. So, I mean, if you focus on traumatic diseases of traumatic origin, originated by floods rather than wind storms or extreme rainfall, it is debatable if indeed the risk is increased after climate change. What is not debatable is that these events can have an influence on the human health. It's clear. A windstorm, a flood have an influence. And I think this is significant for you. So this is why I believe that this is anyway a useful information. So, given that these events are, of course, of climatic origin, there are some organizations that define health indicators that are just climatic variables. And I think another example is, useful example is this one, and now I'm expanding the picture, and it's given by the Global Climate Observing System. It's called GCOS. Let me click on the link and of this figure. Let me see if, okay, it doesn't open directly. I need to go to the website, so let me go out here and go here. And here there is the link. Okay, so this is an international organization which is promoted by the WMO, the World Meteorological Organization, the United Nations, the International Science Council, UNESCO, and in this figure they present their health indicators. And you see here that there are several icons, and if you click on the icons, you get the list of their indications. So, for instance, lightning, or let's focus on something that is more hydrosphere, like river discharge, lakes, groundwater. Let's click on groundwater, and it explains why groundwater is important for health, and it shows the progress for specific region of average groundwater level. Groundwater level is an indicator of groundwater storage. Why it's important, groundwater storage? Because in several regions of the world, water security is ensured through groundwater. And in fact, there are several concerns, especially in Asia, which are related to the hypothesis that people are consuming more groundwater than what is charged. Groundwater recharge takes a long time. It may take like a millennium. So the concern is that overexploitation of groundwater may take 1,000 years to be resolved, to be replenished. And of course, this is a huge concern because it's a very large region. It is affected by water withdrawal, but also by the construction of dams, and it's undermining. It is affected by climate change. It may undermine this overexploitation of groundwater, the water security, and therefore health problems, and also problems for food production, etc. So here you have a lot of sorry. Strange, because you see, okay, you see this, and let me just check.
Groundwater is used for Asia, or?
Yeah, I tell you why we have this concern. Okay, let me just check. I think there is still, I don't. So let me check. Okay, now I see the PowerPoint. So why it doesn't show? Okay, now it shows it. groundwater. And groundwater, yes, there is a graph for Sweden, I think. So if you go back to this figure, okay, here there are a lot of indicators which are divided by sectors, and the sectors are Earth system domains. You see that the spheres here, the Earth system is studied by subdividing the Earth into domains. Cryosphere is the domain of snow and ice. Anthroposphere is the social domain, is the domain of the land that are inhabited and therefore are strongly affected by human impact. Biosphere is the sphere of living organisms. Hydrosphere is the water cycle. And then here you have a focus on specific environment. So physics of surface ocean, ocean biology, biogeochemistry, and ocean physics. So this is another example of health indicators. Okay, now another interesting example is the Copernicus climate indicators. And let me try to open this link. And let me check if it works. Yeah, once it appears. Anyway, the indicators are these ones. And these are climatic indicators, but these organizations propose also to use this indicator to estimate the impact on the human health. And now, more specifically, the indicators of the US Environmental Protection Agency, this link is not opening now, so let's close it. And the US Environmental Protection Agency, this is a very useful reference for you. And you see that here it is focusing explicitly on diseases. And here, this figure, just keep in mind that, let me open it in a new tab. Keep in mind here that they use the term exposure with a different meaning with respect to what we defined. The Environmental Protection Agency identifies with exposure the climatic variables that are affecting our health. So you see, for instance, elevated daytime and nighttime temperature, contaminated water and debris from flooding, and disease-carrying ticks earlier in season and in new parts of country. So you have here on the top the climate impacts, so originated by extreme heat, flooding, and tick-borne disease. Tick-borne disease is a very relevant example of diseases that are affected by climate change. I already have shown to you a graph last time, which shows that the Lyme disease in the United States, the number of cases is steadily increasing. And I said that we are pretty sure that this is due to climate change, even if there might be confounding factors affecting these assessments, like, for instance, they increase the number of animal hosts. So basically, here you have the climate impacts, and then the climatic variables, and then the health outcome. It's interesting to look at the health outcome that they think are important. Heat-related deaths and illnesses. This is interesting because we will focus in the following time of this lecture on specific diseases, gastrointestinal illnesses and injuries. So these are basically waterborne diseases, gastrointestinal illnesses, and Lyme disease, which is the more frequently experienced tick-borne disease. There are several tick-borne diseases, but the Lyme disease is the more frequent.
Okay, why are ticks affected by how is it affected by climate?
Yeah, very good. Very good question. It is shown, okay, later on, but I anticipate to you the reply. Because with increasing temperature, the life cycle is extended in time. So the exposure of the vulnerability of people is increased. Why? Because it's longer the time that we are in possible contact with ticks.
Because it's lifespan.
Yeah, but their life cycle is longer. So basically, they get to the larval stage from eggs to larval earlier in spring, and they continue their activity for a longer time during the fall season. Usually, we are in our climate here. We were used to be careful about ticks from about April to October, and then we know that with the cold temperature, they die. So, and now the risk is our vulnerability. The number of exposed people is higher because our vulnerability goes from February to November. It's more extended. This is one of the reasons. But as I said,
So they don't die. That's pretty.
Yeah, they live longer. And this is the case for several water vector-borne diseases that, also COVID-19, I am planning to discuss it today. There are some people, some scientists who are convinced that with increased temperature, there is an increased risk of a species jump because it's the life cycle of several animals and several viruses is more extended in time during the season. So the seasonality of our vulnerability to these vectors is changed. Depends on temperature, so it is changed. Indeed, also the river flow is changed in seasonality, and therefore it's clear that all of these illnesses, which are characterized by a strong seasonality related to climate, of course, because seasonality means climate, their dynamics is changed, also for the flu.
And also something that you said earlier about the groundwaters. We said that they are used more than they are recharged.
Yeah, okay, I forgot to say.
But this is in Asia.
I said Asia because groundwater has a problem. We cannot see it. We cannot monitor it. The only thing that we can monitor is the groundwater level into the wells. But it is not a synonym of water volume available. So we cannot really see how much water there is in the underground. What unfortunately sometimes happens is that we use this groundwater and suddenly it disappears. And or suddenly it becomes salted because of the intrusion of salt water. But there were several researches starting about 20 years ago related to the measurement of gravity. 20 years ago, with the GRACE experiment, G-R-A-C-E, the GRACE experiment, they started to measure gravity with satellites. Just 1 second, I want to get here. GRACE, gravity map. Okay, so this is one. It's a NASA, a NASA project, and this is one of the animation. They measure the gravity. Gravity is not constant over the Earth. We take a constant value by convention of 9.81 meters per second squared, but actually it is varying. And gravity is originated by the mass of the Earth. So where the mass of the Earth is heavier, there is more gravity. Where the mass of the Earth, which means also specific weight of the soil of Earth itself is higher, you have more gravity. So where there is a lot of groundwater, there is more mass because water is filling the voids. So what are the voids in the soil are filled up by water. So the mass is increased. So we expect an increase of gravity where there is more groundwater. And what they found with this project is a decrease of gravity in Asia. And how can we explain it with the groundwater overexploitation? Which means that we assume that by overexploitation, it is decreased the volume of water in the underground. And of course, there are several questions related to that, which are basically related to uncertainty, but it's a clear indication. And this is why I said Asia. There are a lot of papers. If you look on...
why do they use that much for some purpose?
Because the water demands are increased all over the world. And in Asia, the construction over the big rivers like Tigris, Euphrates, of dams upstream may have has caused for sure a decrease of the river flow downstream. It may be, but of course, these are hypotheses. It may be that people that were used in the past to get water from the rivers, now, today, in a situation where the water demand is increased, maybe that they are overexploiting groundwater. But the same concerns are, for instance, experienced here in Italy, in the Padana Plain. I know the problem quite well. About 20 years ago, they experienced a lot of decrease in groundwater level and then a lot of subsidence because the water demand increased and therefore people increased the extraction of groundwater, the groundwater withdrawal. And then what they did is to build new water withdrawal plants on some rivers like the Reno River, the Seta River, and the main water supply systems are now fed by more and more surface water, and they decreased the use of groundwater. And if you look at the groundwater level in the Emilia-Romagna region, they are public, they went up in the past 20 years.
Isn't it too dirty?
Sorry, say again.
Isn't it too dirty? The groundwater.
The groundwater, you know, there are situations where the groundwater is more expensive because you have to pump it. So when you have water from rivers is cheaper. On the other hand, water from rivers may be contaminated. It's easier to contaminate a river than a groundwater body. On the other hand, the river is easier to recover. So basically, it's easier to recover the contamination of a river than the contamination of a lake or a groundwater body. But usually what people do is when they have surface water available, they try to use it because it's cheaper. But when they don't have it, of course, they use groundwater. But the problem is, you know, groundwater, we have to be very careful. Anyway. Okay, let me make 5 minutes more and then I make a break. I think with the health indicator, we may close here and then use the last 2 hours to discuss in detail of specific illnesses. I just want to make a final discussion before I make a break. And the discussion is related, I already started it, to the effective influence, impact of climate change over human health. I already said, look, this is debatable. And it is debatable because it is even debatable the fact that extreme events are increased. As I said, we are sure that climate change is causing global warming, but does this imply an increase of the frequency and the intensity of floods? This is still not sure. And therefore, you understand that even for human health, there might be some impacts that are more clear, like the impact of heat waves. On the other hand, there are other impacts that are not so clear. And also for those that are clear, Keep in mind that for many regions of the world, it's not a big problem because where we have air conditioning, of course, it is like a vicious circle because air conditioning means CO2 emissions. But where we have air conditioning, the impact of higher temperature may be mitigated. And very often, when these assessments are made, we forget about the health benefits which may derive from climate change. For instance, if you think the decrease of cold waves are also dangerous. So on the one hand, of course, we have an impact due to increased temperature and therefore increased exposure of people to warming. On the other hand, we have a reduced impact of cold waves. And there are other illnesses which, with a higher temperature, are less concerning. We know that in general, the health of people is more affected by cold weather, by cold rather than heat. People usually are more healthy in a warm environment. And these benefits are actually not often considered. There has been a paper published in Nature recently that pointed out these issues and also pointed out another consideration, which I think it is extremely interesting. When we make predictions on the health impact of climate change, usually we don't make any assumption on the improvement of the healthcare system. Actually, human age is life expectancy is steadily increasing, and there is no reason to question, there is no reason to exclude that this increase will continue into the future. I mean, it's clear that the human development has an impact on climate, and therefore there is an impact back to humans. On the other hand, the human development is beneficial for our health for many reasons. And therefore, I mean, these predictions may be overly pessimistic. So I am essentially teaching climate change. I am much concerned by climate change, but I also want to be very realistic. So it's clear that climate has an effect on the health of people. But if I'm not really sure that it may have an effect that is so extended as some alarmistic reports tend to say. And in general, for climate change, I think the scientific community may have made a communication mistake because I think there was an exaggeration of the concern in order to convince the public that climate change is a problem. So in order to convince people to make an effort, I think that some scientists tended to be too much alarmist, too much alarmism. And I think this may be detrimental because it may undermine the public trust in science. It's like issuing a warning that doesn't turn out to be true. And people lose the confidence in science. And I think this might be the reason why a recent poll in the United States showed that the number of concerned people by climate change is decreasing. So this is something that I wanted to report to you because as people that in the future may be responsible for managing health at the global level, I think you need to get an objective view. For sure, climate change is a problem. For sure, this problem is impacting humans in several ways, and I think it's important to establish priorities. Okay, how can climate change impact on health be mitigated? I think it is nice to look at this graph. And this is, I don't think I have shown to you it before. These are emissions, global emissions of CO2, of greenhouse gases. And you see the contribution of different sectors here. If we want to mitigate climate change, we need to reduce these emissions. I think it is interesting to know what is our best belief on the subdivision of our emissions in different activities. I said that to the best of our belief, because you understand that getting these numbers, there is a lot of uncertainty. How can we really quantify how much greenhouse gases, the volume of greenhouse gases that we emit at the global level for transportation, for instance? But this is the best of our belief. These are public numbers. Our working data is our public data that you can get. There are a lot of statistics also on health. These are public numbers evolving. This was downloaded like 2020. And so, for instance, I just want to tell you a couple of considerations which I think are inspiring, like electric cars. We know that there is a push for electric cars. I think it is really the future for many reasons. Because, for instance, if you think at the PM 2.5, the air pollution in the cities, which is proved, statistically proved, the reason of cancer. I mean, this is related to car emissions. So reducing the use of fossil fuels is indeed very important for the health of the urban environment. But in terms of climate change, it is debated the fact that if we use an electric car and our energy is responsible for 70% production of energy of our emissions, here transport is here. Transport is 16%. I mean, 16% of our emissions, and this is going to increase because if we use electric cars and energy production is still obtained mainly through burning of fossil fuels, this is a problem. Or another, I mean, is it already the right time to push towards electric cars? In a urban environment, yes, but in terms of CO2 emissions, for sure in a urban environment, our health gains a lot, but not for climate change. It gains a lot for the reduction of PM 2.5. But for greenhouse gases emission, is this the right push, or should we wait a little bit? Should we wait for the development, the deployment of the derivation of energy from hydrogen, for instance, because this is going to materialize in maybe 10 years. So is it now the right time to push for electric cars in terms of emissions? And another thing, very often we are told that we shouldn't take the plane and we should take the train to travel. But if we look at the percentage of aviation, it's 2% of our emissions, 2%. And energy, if we take a train, I mean, and the train uses energy, I mean, you understand that there are some considerations that we need to make. And second thing, energy is something that is indeed important, and we can't live without energy. I mean, either we find a way to make energy in a clean way, or we need to postpone our commitment to reduce emissions, because this is something that we can reduce our energy consumption, but if we push for electric cars, it's not easy. And also now we are pushing for using energy also for heating the buildings. Agriculture, forestry, and land use is the second, 20%. And agriculture means much of these emissions are given by meat production.
Professor, could you repeat the part about trains and planes? We said aviation is almost 2%. How much was the train?
The train uses energy. And therefore the question is, if you don't take the plane, let's suppose that with the plane you remove that 2%, you just cancel aviation, and then everybody takes the train. So what is the impact on energy? So,
rail.
Sorry?
I think rail.
Yeah, rail, it's somewhere here, and 0.4. Yeah, but if we remove the planes, and how much will increase the rail, because there will be an increase. And maybe, I mean, maybe that it's convenient, but if you remove the plane, you remove 2%, and if you if you increase like 0.5, you gain just 1% of less emissions, and it's not really the solution, I think.
And also maybe road transport.
Road transport is much important, but road transport is mainly dominated by trucks.
Oh, okay, not trains.
No, not trains. And the most important part of emissions for road transport is trucks. And trucks, yeah, it's a problem because also we need to trade. Okay, this is another example. And this is interactive. It's on my website, but it is interactive. Greenhouse gas emissions by sector for the world, but you can change the country and you can explore, you can get the table, you can get the chart, you can play with it. So if you go in Afghanistan, it's a completely different story. It's agriculture that is the major emitter, and then the other ones are less important. And if you go in Italy, it's more similar to the global average. In Italy, it's electricity and heat, the most important, and then transport, buildings, etc. Sorry? Yeah, for sure. I think it is similar to Italy. Let's see. Electricity, it's similar. But there is, in Turkey, there was a larger increase in electricity and heat, yeah, but I think it's just a different timing of, and then you can also, different timing of changes that have been made. You can zoom here. This is really interactive. It's linked in my website, but actually, if you go to our World in Data, you get a lot of charts of this type. Okay. Here there is a critical synthesis, but I don't think we need to make it. It's just a summary, and just keep in mind of the train of thoughts. So climate change, health determinants, and health status. Okay, good. I would say that now I would make a 10 minutes break, and then we go with the diseases. Okay, so climate diseases. So there is a PowerPoint even here. Climate-related diseases. Okay, I prefer to use it not in presentation mode because otherwise it stalls to me the screen sharing. So, train of thoughts. These are the diseases that I would like to discuss with you, and we have about. No, sorry. No, I just was asking if you need that I stop a little bit. Okay, very good. These are the diseases that I would like to discuss with you. I'm not sure we have enough time because what I'm proposing to you is now to run up to 6:15, so end of our time. And I'm not sure we have enough time to discuss all of them, but the discussion is fully reported in the web page, which is here. And if I run out of time, I will I will tell you instructions for use in order that you can read them if you're interested. I just want to make a premise here, and the premise is that the literature is evolving and it's still very scarce. There is no much contributions, and most of the literature, most of the references that I found are qualitative. They are not discussing, with few exceptions, in detail, because there is still a limited awareness of what are the most important diseases that can be affected by climate change. And so I made a selection basing on policies that I found. So I thought that the best approach in order to structure our discussion is to focus on policies that some organization have set up. And just keep in mind that in some of the cases, I think there is, again, too much alarmism. But on the other hand, I think that, as I said, the connection between climate and these diseases indeed exists. And I thought that it is interesting to explore it. So these are the diseases that I want to discuss with you. First of all, I will make a premise on non-communicable and communicable diseases. And in particular, I want to make a premise on waterborne diseases, which are extremely important in our context because they are strictly related to the water cycle. They are strictly related to water, and then the water cycle. And the water cycle means climate. And then I want to make a focus on some specific diseases: COVID-19, cardiovascular diseases, respiratory diseases, neurological disorder, mental health, and skin diseases. In the policies that I found, the list is longer, and there is in my website the full list, and there is also the reference, the link to the policies that I consulted. I think that here there are some of them that are more important than others, some of them for which the impact of climate change is more significant. And what are these? I would say that first of all, communicable diseases. Because communicable diseases are infectious diseases, are vector-borne diseases, which means that they are affected by water, they include waterborne diseases, and they are related to the vector. And the vector very frequently is a living organism, which is affected by climate. Non-communicable diseases, there is some literature. I think the important ones are the traumatic injuries related to events like floods, which, however, I think their treatment is much similar to the treatment that you already know for these specific diseases. So for a traumatic injury, depending on the type of trauma, you know what is the therapy, what is the treatment, what is the approach. And it doesn't make any difference, in my view, if the trauma is caused by climate change rather than, for instance, a car accident. And for this reason, I'm not focusing much on non-communicable diseases. I just want to say that, as you know, the injuries, incidents related to those natural hazards that we think are affected by climate change, the injuries are many, are frequent. So if we think of floods, if we think of dam break, if we think of windstorms via the Baia storm, for instance, the Baia windstorm, there are several deaths, several injuries. So I think the issue is relevant. On the other hand, as I said, I don't think that we can say much more of what you already know, depending on your specialization. Cardiovascular diseases, I think that indeed during events related to climate change, we experience a lot of them. And during windstorms, during snowstorms, during floods, there is quite a significant incidence of cardiovascular diseases. And Another thing that I really want to emphasize is mental health. Mental health disorder caused by climate change is a big issue, in my opinion. And it's not a big issue for climate change itself. I am convinced that it's a big issue because there is climate anxiety, which is more and more diffused. And I can really touch it because I see that even among students, it's increasing. And I mean, it's something concerning. And eco-anxia, and you may know that there is an increasing manifestation of these issues. I would say that this is much more concerning than neurological disorder. Yes, Parkinson and multiple sclerosis can be affected by climate change, but I don't think the effect is really relevant. And also for skin diseases, I wouldn't say that this is a big issue. Okay, let's try to, first of all, to make some premise. This premise is just related to a first premise, which is not here, but it's in my webpage. It's non-communicable diseases. They are very important, but I think you know these issues better than me. So the premise is just to emphasize that non-communicable diseases are responsible for the majority of the deaths in the human population. Also, they are responsible of premature deaths, and so they are indeed important. But as I said, I think this is already part of your background. And the premise, non-communicable diseases, I want to take some of your time because I think it's particularly important to explain what we mean and to explain why I believe that indeed they are much related to water. So vector-borne diseases are caused, as I said, by living organisms. And therefore, they are, first of all, much diffused, and more than 700,000 deaths every year at the global level. And the diseases are, the examples are here. And let me go back. Malaria, dengue, schistosomiasis, human African trypanosomiasis, leishmaniasis, Chagas disease, yellow fever, Japanese encephalitis, and onchocerciasis. And in particular, the encephalitis are vector-borne diseases that are related, some of them are tick-borne diseases, and in particular the Japanese encephalitis. And I mean, they are really strictly related to climate. And here you see a summary in this table of reported case counts of notifiable, pronunciation is, when I get tired, notifiable vector-borne diseases in the United States. And you see 2013 and the median range in 2004-2013. It is interesting to compare the 2013 reported cases with the median range, 2004-2013. And you see that for Lyme disease, I mean, in 2013, there has been a significant increase, is much larger than the median, which was the number of reported cases is 36,000, and the median was 30,000. And here there are other examples, and you see that in general, the reported cases of vector-borne diseases, the first 6 rows are tick-borne, and then you have mosquito-borne. You see that there has been, in general, an increase which took place during the onset of global warming. So indeed, it's clear that there might be some confounding factors, but on the other hand, the numbers are coherent. So it looks like, indeed, this change in seasonality, this increase of temperature had an effect. In particular, the Lyme disease has been widely studied because some of these diseases may have important consequences. Fortunately, for some of them, we can, in most of the cases, we have means to mitigate the risk, but it depends on the country, it depends on the state of the healthcare system, it depends on the local conditions, once again. And of course, the United States is a lucky situation, lucky is not the right term, is a favorable situation for putting in place mitigation actions. There are other countries where it's the conditions are not so favorable. Okay, so waterborne diseases, I want to spend some time on this because there has been a lot of literature on climate change and waterborne diseases. And this is one of the links between climate change and the health that look more trustable, more robust, to use the term that we discussed before. And of course, waterborne diseases are also related to water treatment, water sanitation, and because we know that waterborne diseases have been widespread since the development of urbanization. Cholera and the pest started to occur in Europe when the size of the cities increased, for the reasons that you can see depicted here. For the fact that people were using groundwater, they were using shallow groundwater, so groundwater that is not very deep, and this groundwater gets easily contaminated by human wastes. Today, we don't use any more shallow groundwater for water supply for civil use. We only use deep groundwater. Today we have standards, and today we are treating the wastes. We are avoiding to release the wastes into water bodies, into the ground for this very reason. And but still, I mean, waterborne diseases are sensitive to changes in water cycle, to changes in water resources availability, to changes in river flow, because also the efficiency of water treatment plants depends, and also the concentration of pollutants depends on river flow, depends on dilution. And therefore, still, these are a matter of cost. Most of the literature on climate change and waterborne diseases focused on the pathways for contagion, because contagion is related to the movement of the hosts, and the hosts may move, if they are humans, they may move along roads, so road network, or if the hosts are ecosystems, living organisms different from humans, they can move along the river network. And water, which is the vector at the end of the story, moves along the river network. So there has been a lot of studies studying the statistics of contagion and the statistics of recovery by putting together the connections between the hosts and the humans along the communication paths. And the communication paths are, for instance, river network, mainly river network and road network. So there has been a lot of contributions on that. Okay, now, waterborne diseases may be vehiculated by protozoa. I think, once again, you are better prepared than me on what are protozoans, and they are may be free-living or parasitic, and they feed on organic matter, such as other microorganisms or organic debris. And here you see a collage of images of protozoans from Wikipedia, which you'll find also on my webpage. And waterborne diseases can be vehiculated by bacteria, which are microbes, as you know, with a cell structure simpler than that of many other organisms. And the most classical example of bacteria is the picture that you can see here, Escherichia coli. Escherichia coli is causing, as we know, several diseases, including diarrhea and other diseases, which we will discuss in more detail. And let me just make a check along the web page if I am not forgetting anything. Okay. Here we are. Perfect. Okay. Now let's make a focus on Lyme diseases. This one is to be closed. One second. Okay. Let's make a focus on, okay, I forgot to mention waterborne diseases by viruses, and there are many of them, and there are also waterborne diseases caused by metazoan parasites, and including nematoda or schistosomatids, and flax, etc. And this is just a list. Let's focus now on waterborne diseases, vector-borne diseases in detail, and in particular on the Lyme disease. Okay. We discussed before about why the Lyme disease is increasing in cases. And here you see a picture of the life cycle of the ticks, which also shows the phases in which human can be exposed to Lyme disease, and some of the changes in seasonality expected with climate change. Okay, here you also see the source. So let's look at seasonality. We have an earlier spring and a later fall, which means that the green color that you see in the top of the circle, spring, is expanding toward the left. And the orange color in the right of the circle, summer, is expanding into the fall. Okay, so what is the life cycle of the ticks? The eggs in early, late spring and summer becomes a larva, and then in the fall season, during winter and during spring, the larva, in again late spring, evolve in nymph, and during the summer second year, they get in touch with hosts, and when they are in the state of larva, they can get in touch with the small animals like mouses, like birds, and when they are in the state of nymph, they get more easily in touch with the humans. And it is very rare, the contamination in humans in the state of larva, because humans get in touch with the ticks when the ticks reach the humans. So when the ticks are in the state of nymph and they walk and can bite the humans. In the state of larva, humans don't eat eggs of ticks. It's very unlikely, because we are generally careful to wash our hands, etc. While when they are in the state of nymph, we can be careful, but we cannot avoid to go outside. And even if we use sprays, even if we try to cover our body as much as possible, it's very likely to get in touch with them. And usually they get in touch with the humans starting from late spring. So typically here I start to be concerned. I like to go outside. I like to hike. I like to climb. So I am very often within very wild environments. Not very wild, but I mean, I am outside. And I start to be concerned in April, more or less, after maybe some rain, some spring rain, because they evolve in the state of nymph with the help of humidity. So the best condition for them is humidity plus warm weather. So late spring is perfect, and then summer. During summer, they complete their life cycle, they become adult in fall, and then they produce the eggs during the winter. So you understand that if summer is expanded, if the fall season is expanded, if the winter season is reduced, the exposure of humans, the risk of human infection is greater, is longer, is extended over a longer period. And this is why we believe that the risk is increased, is augmented, and the number of cases actually is augmented. Of course, one may say that, as I said, there might be confounding factors, and in particular, the increase in the density of intermediate hosts like mouses and birds. Okay, this same reasoning can be applied to several other vector-borne diseases. I go into the details for the Lyme disease because it's concerning, first, because it's widely studied, because it is concerning, and because it is, I think it is representative. You can get the same approach for other diseases. Okay, perfect. Now, interesting to say, somebody thought to model the cases of Lyme diseases. Somebody tried to find an analytical expression to reproduce, to simulate the case of Lyme diseases. Of course, we have data. So with the data, we can produce a model and we can estimate the model parameters. The idea was to use a parametric model, which is very simple. I think it is an interesting example. You have also the reference. It's an open access paper. I think it is an interesting example because it can be extended to other vector-borne diseases, provided we have data and provided we have an idea of the relevant variables to include into the model. The model is a mathematical expression that has to relate causes to effect. The effect is our data, the number of reported cases. We have to gain an idea, we need to gain an idea of the causes. So this model is very simple. It's actually a linear model, which is expressed as low is the number of Lyme disease cases, okay? And of course, the number can be expressed, can refer to a region, can refer to a country, can refer to different contexts. Of course, you need to make sure that the process is in a way homogeneous in space, because if you relate, for instance, the number of cases to the onset week, like in this case, and you have a completely different seasonality because you may move to the southern hemisphere, for instance. Of course, you have to change at least the definition of the variables to be included into the model. Usually, when we apply these models, we collect the data in a region, and then we take the numbers of that region and try to reproduce them. Okay, so we have an intercept, which is this constant value of 17.563. And then we have these explanatory variables where GDD W20 is the cumulative growing degree days from week 1. A thick growing degree day is identified by a mean value of daily temperature above 10 degrees centigrade. Okay, so this means that I start from week 1. Week 1 is the first week of the year, and then I count the number of days with the mean value of daily temperature above 10. Okay, and this is GDD with the subscript W20, and the coefficient is negative. It means that you have a negative for increasing GDD W20, you have a decreasing number of cases. Now, we have instead a positive correlation with SDM5. SDM5 is the mean saturation deficit in the atmosphere in millimeter of mercurium in the 5 weeks before the onset week, which means that the deficit of the atmosphere is the saturation deficit. It means that the lower SDM5, the more saturated is the atmosphere. Okay. PRCP AW8 is cumulative rainfall in millimeters from week 8, and this has a positive correlation. This is distance in decimal degrees to the Atlantic Ocean coastline from the weighted mean center of each state's total Lyme disease cases. This refers to the United States. So basically, they identified the geographical variable. They identified, low is Lyme onset week, is not the number of cases. This is my mistake, because there is another equation explaining the number of cases, but low is the Lyme onset week, so not the number of cases. This explains the negative correlation, meaning that you anticipate the onset. Onset is the week where you start seeing the cases. So this is describing the timing of the cases. Okay, so basically, as I said, low onset week, and the causes are cumulative days with temperature above a given threshold, and then we have the humidity of the atmosphere, and we have a geographical, well, we have a cumulative rainfall, which is extremely, because they need rainfall in order, they need humidity, and then a geographical parameter. The model performance actually was quite good. The R square is close to 0.8. R square is an indicator of the goodness of a linear regression, goodness of fit of a linear regression. It ranges from 0 to 1, and 1 is perfect interpolation by the linear regression. 0.8 is a good model. I mean, in hydrology, when we try to model flat flows, when we reach these kind of R squares, we are very happy. So the critical week is anticipated by large values of GDT, which means warmer climate, while it's delayed by higher saturation deficit. Saturation deficit means that if it increases, the atmosphere is less humid, so it delays the onset. Cumulative rainfall is higher rainfall usually corresponds to lower temperature. So in this case, they found indeed that higher rainfall causes a delay. And because I think that the humidity is taken into account by the saturation deficit, and increasing distance from the coast delays the onset, because usually it has an effect also on the humidity of the atmosphere. In this model, I can recognize a kind of point of attention. I'm not really sure that these drivers, these independent variables, are independent. If they are not independent, then the linear regression can be a little bit misleading. So in specific, I think that the distance from the ocean may be correlated to the saturation deficit, and the saturation deficit may be correlated to rainfall. So what may happen here is that you get the saturation deficit accounting for the effect on the onset week of humidity, but humidity is caused by rainfall. So it means that while we find here that rainfall is delaying the onset week, maybe that if one removed SDM5 from this relationship, the sign of PRCP becomes negative. It may happen. It may happen because if we remove humidity, maybe that rainfall has to compensate for it. Actually, I think that with the same temperature, if you get more rainfall, the onset is anticipated rather than delayed. Here you can get an effect of delay because humidity is taken into account by the saturation deficit. But if you want more details, there is the paper. I think this is a very simple model. It's a linear model. The linear model, by definition, is the more robust model. So, and coming back to our considerations, very often why a non-linear model is not used, even if you use a non-linear model, you reach a better interpolation. So if you have observed cases, if you have the result of an experiment, and you identify explanatory variables, if you use a non-linear model, for sure you reach a better interpolation, because the linear model is a simplification. On the other hand, when you extrapolate outside of the range of the data that you have collected in your experiment, it may happen that the non-linear model makes big mistakes. And this is why people, when there is uncertainty, they tend to use these very simple models. And this is why I think this is a good example to represent other numbers besides the Lyme disease. Of course, if you want to extend to other illnesses, you have to change the drivers. What you see here, basically, it's that the drivers are strictly related to climate. And if you make a change of climate, and in particular, if you warm the atmosphere, you have a change in the saturation deficit, because a warmer atmosphere means that the concentration of water at saturation increases. And if you warm the atmosphere, you have, of course, higher temperature, and therefore GDD-W20 increases. And clearly you can see that the onset week is anticipated, which means that we start to be exposed to risk earlier.
Professor, could you repeat the interpolation and extra?
Yeah, okay. Yeah. Mm-hmm. Good. Okay, let's suppose that you have here a plot with let me think of an example that maybe okay. So let's suppose that we have here the line offset week. So I refer to that example, and let's suppose that here we show the relationship with the GDD-W20. Okay. Of course, we are just showing the dependence here on GDD-W20 just for simplicity. I could make the same graph with respect to the other variables. And it's GDD-W20 is the cumulative growing degree days, the cumulative number of growing degree days from January 1st. So the number of days, okay? And you get some points here, which are the results of your experiment. Okay, so given that it's a negative correlation, I think that you may get points like this. There is uncertainty when you collect this data, okay? Okay, now let's suppose that you have just these 5 points. You can decide to interpolate these points. Let me take this here with 2 models. You can take a linear model and the linear model is like, I think the best linear model here is this one. Yeah, it's not very straight, but let's assume that it's straight, okay? And of course, it's not perfect. Or you may get a nonlinear model. The nonlinear model probably would do something like this. Because you introduce some exponents. So if you look at the performances in reproducing the crosses, the nonlinear model is better, for sure. Now, let's suppose that you want to extrapolate. Extrapolate means that you go outside the range of the results of your experiment. So if I extrapolate the linear model, I go here and there. If I extrapolate the nonlinear model, depending on the value of the exponent, you may get something like this. And something constant here. Now, our experience shows that you have a very limited chance of getting the correct nonlinear model, because nonlinearity is really, when you go, has really a pattern that tends to give asymptotic values that tends to diverge. The nonlinear model has a pattern that tends to diverge. So it is extremely unlikely that with few observations, like in this case, you get the correct pattern, even if the pattern is better than the linear model to reproduce the observed point. So what I mean is that it's much more likely that you get something if I got further observations that, for instance, it's here or it's here, rather than close to the nonlinear model. And you may say, how can you say that? Because there are several studies that made experiments, and these studies concluded that the linear model is more robust, meaning that when you extrapolate, which means going out of my observed data, because these ones that I added later are not available when I fit the model. So when you have few observations, it's safer to use a linear model, and this is why in this study they used it. But we also do that in hydrology in several scientific, in several scientific applications, because there are studies in statistics proving the robustness of the linear model.
But it's better in interpolation, but worse at extrapolation.
Yes, this is correct. And usually we are much interested in extrapolation. It depends on the science, of course. In a flood science, we need to extrapolate. And why? Because when there is a flood, we cannot measure the river flow. And therefore, to make a flood prediction, we need to extrapolate. And this is why hydrological models are linear or quasi-linear, but the hydrological models that are used for making a technical design are very close to linearity. Okay. Here there is the conclusion of the study, which I don't think we need to discuss. I don't think we need to discuss this because basically it's easy to consult. It's not an information. It's very specific. It's Lyme disease in the United States. And anyway, let's look at the last sentence. The results of the present study suggest that 21st century climate change, particularly increasing temperatures, will likely make environmental conditions suitable for earlier onset of Lyme disease cases in the United States. And this is what this graph says. But I really don't think that you need to look at this paper. I think it is an interesting example of how you could set up an analogous model for other climate-related, in this case, temperature-related diseases. Maybe something that you can try yourself. For several illnesses, you have public data that are available. Okay, perfect. West Nile virus, not many details here. I don't want to give many details. I just want to say that it's considered to be affected by climate change because it's a vector-borne disease that is much diffused, and there are natural hosts, birds, and insect vectors, mosquitoes. And it is the number of cases is increasing, and you see here, and from 1999 to 2013, a total of about 1,400 cases were reported in the United States. Annual variation is substantial, both in terms of case count and the geographic distribution. And because it's transmitted through cycles of infections between birds and mosquitoes, we believe that it is affected by climate change, and in particular by, as you read here, the effect of temperature and humidity, and then precipitation on the life cycle of birds and mosquitoes. Again, raising temperature and raising humidity are expected to increase the onset of West Nile virus. And I didn't find any modeling experience, but I think this is quite an important disease, so I think there might have been experiences. Vibrio. So here we are moving to bacteria, and I think it is. I think you have already a very good knowledge of what bacteria are. Correct? Yeah. Perfect. So I don't think we have to discuss what they are. And just forgive me because I'm also teaching to other schools other than medicine. Yeah, you have to say, you don't see it. Yeah. You have the slide in your PC. Yeah, okay, I understand. But still, I think it's better if you all can see it. So this is, let me just move to the website. Okay. This is a conceptual diagram from the United States Global Climate Research Program, and which focuses precisely on the links between climate drivers and health outcomes from bacteria, and through exposure pathways, and through the environmental and the institutional context, and the social and behavioral context. What is significant to say here? I think it is this figure is significant if you had to identify the independent variables for a model. So, I mean, in the case of the Lyme onset week, we considered only climatic variables. But as you can see here, there are also other variables which social variable, environmental variable, which may be important. We already pointed out this in our previous lecture. I just wanted to make a specific discussion on the bacteria. And Vibrio are aquatic organisms, and therefore in this case, our considerations, which we made before, on the importance of the structure of the river network, the importance of the water flow, both in surface water and groundwater, is relevant. It's extremely important if we want to describe the pattern of contagion and the pattern of recovery. Here we need indeed an interface with the science that studies the water cycle, which is hydrology. And in particular, depending on the state of the water supply system. And therefore, here also engineering comes into play. When I study these problems, because it is quite frequent that engineers are called to study these problems, not in relation to climate change, but in relation to the spread of possible contamination. So there are public institutions that often refer to universities for getting a consultancy on estimating the vulnerability of the water supply system to contamination, to water shortage, vulnerability in general. And what we do in order to make an assessment as a first step is to get the information on the water sources. And you may think that this is an information that is readily available. Actually, it's not so readily available. Water managers themselves very often cannot provide a quantitative subdivision of the water supply volume that they dispatch in terms of water sources. They are able to say, okay, we have a spring, a huge spring, and then we use wells. We also have a water supply from a river, but when they have to quantify the volumes, they often don't find numbers. They don't have numbers because water supply is the result of a continuous evolution and adaptation to increasing water demand and climate changing, because climate is always changing. So basically, basically on their needs, they move forward. And keep in mind that up to 30 years ago, there was no digital memory. So everything was stored in papers, and after a while, the papers are not available anymore. It just suffices that the office is moved. When the office is moved, this is a disaster for the historical information, because usually they destroy the information. This is still happening in some cases, because much of the information is on paper. You shouldn't be surprised to know that for many bridges, but not only in Italy, also in the United States, for the majority of the bridges existing, we don't have any information on the foundations. So they have the foundations into the river. We don't have any information anymore because the information was stored in 1950, 1940, almost 100 years ago, and then maybe the office moved, and the competence, the responsibility for the bridge moved from one administration to another one, and there is no way to get information. So this is why, for instance, in Italy, several bridges are completely unknown, and it's considered to be an emergency, to become like an emergency, because some of them collapse suddenly and in an unexpected way. So this is the reason why the National Authority for Road Transportation is starting investigation, systematic investigation of the state of all the bridges, because they don't have information. And for this case as well, as I said, water supply systems, very often we don't have any information on how they work. And the first information is, where do water come from? Where does water come from? So it's from groundwater. Okay, what is the depth of the well? And this is information that I asked recently. Okay, you have several wells. Can you please give to me the stratigraphy, which means the geognostic inspection of the well, the depth, how many windows, because the wells typically have many windows, meaning that they are getting water from different depths. And we need to quantify what is the depth, what is the exposure to contaminant. Depth means exposure to contaminants. And then we try to decipher the pattern of contagion and recovery. Also recovery, because of course groundwater can be recovered. Okay, here there is an interesting table, I think, health outcomes that can result from exposure to agents of water-related illnesses, including Vibrio. And so here you have the pathogen or toxin producer, the exposure pathway, so what is maybe shellfish, fish, recreational waters, drinking water, and whatever, and selected health outcomes and symptoms, and major climate correlation. So let's focus on the first one, algae, Toxigen marine species of Alexandrium, Pseudonychia, Dinophysis, Gamberdiscus, Carenia brevis. The exposure is given by fish, shellfish, recreational water, so people may get in touch with the algae while bathing, and then it causes gastrointestinal and neurologic illnesses, etc. And the climate correlation is temperature, increased water temperature, which favors the blooming of algae, and ocean surface currents, which change with climate change. Much difficult to predict the future of ocean currents, ocean acidification, and the fertilization of waters, which means algae blooming, and hurricanes. I think this table is interesting because it gives to you also an idea in order to develop health indicators. It gives to you an idea of the connections. And this is what it's the education which I hope to leave to you, an understanding of the links and their importance between climate, health indicators, pathogens, health outcomes, and at the end, human health.
So which one did you mention? For the first row?
Yeah, algae. I'm not reading everything because I don't think I'm not interested in a particular case. I'm just interested in the concept that you get the concept of exploring, understanding the links and exploring them. And here is a figure that I found it's very nice, but it doesn't say anything more with respect to what we already introduced. This is changes in climate and effect on river and water demands, etc. And this is the effect on the nutrient cycling, sediment exchange, groundwater, and nutrient and contaminant loading. Again, nutrient cycling. This is extremely important for the life cycle of the living organisms, and also the life cycles of the bacteria and the ecosystems in general. And this is much influenced not only by climate change, but climate has an influence on the nutrient cycling. It's also influenced by agriculture, fertilization, and the discharge of sewer systems, etc. Just keep in mind in this discussion that how the sewer system works. A typical sewer system, a so-called combined, a traditional one, combines the human waste, the delivery of human waste, with the delivery of the water that is drained by the streets. So it combines what are called the gray and black waters, which are contaminated by human wastes, with the so-called white water, which is drainage water, which is supposed to be cleaner. And they are combined. The reason why they are combined are manifold. First of all, there is a reason of simplicity. You don't need to build separate pipes, but you just use one. Second, the clean water may help to wash the pipes that are, there are debris, sediments related to the most contaminated water. So when it rains, there is a flash of water which washes the pipes, which is beneficial. The problem is that the water treatment plant, and keep in mind that Milan got a water treatment plant, I think it was 1989 for the first time. Before that, Milan was just releasing the wastes into the Lambro, yes. And then the Po River. When they built the water treatment plant, and in Italy this is systematically about 30 years ago, we realized that the water treatment plant couldn't have the capacity to treat all the water, including the drainage water, because the drainage water is like 1 order of magnitude larger in volume than the human waste water, the black water. So the white water is like 10 times larger in volume than the black water. So we couldn't design a treatment plant that was optimized for delivering, for treating all the water delivered by the combined sewer system. So the idea was, okay, I designed the treatment plant for the black water, and when there is the overflow coming from rain, this is released in the river network without treatment through overflow. And the idea was that the overflow should occur when the dilution is large enough so that the concentration of contaminant is low. But this mechanism, as you can understand, doesn't work perfectly. So it happens quite frequently that the combined sewer system delivers into the river network water that is highly contaminated. And therefore, only recently, but this is really only for the buildings that we started to build like 20 years ago in most of the cities in Italy, we decided to split the sewer system, and it's called the split sewer system, meaning that we have a pipe for the rainwater and a pipe for the human wastes, which requires quite important maintenance for the human wastes. So, understanding the structure of the sewer system is essential in order to decipher a useful health indicator. And this is particularly important for Vibrio. Let me just spend a few words on COVID-19. COVID-19 is affected by climate change. Okay, in a way, you know that COVID, like flu, is sensitive to weather. So, I mean, it's not a question, of course, with a warmer climate. In general, we expect that the impact, the onset of flu or COVID is higher during the cold season. Actually, for COVID, it's not very clear, as you may know better than me, because you know that there have been also onset of COVID in warm season. So COVID is different from flu in that respect. Sometimes we had an expansion of the cases also during summer. But I don't think this is an interesting question. The interesting question is whether the species jump, let's admit that COVID was originated by a species jump. It's not clear, as you know, the debate is still open. But the interesting question is, anyway, with climate change, it's easier that we get a species jump. You know what I mean with species jump, correct? Okay. Sorry? Spillover. Yeah. Sorry, spillover. Spillover is more correct indeed. I would say that it may be, but I don't think actually. But this is my opinion, because you may have seen a recent interview by Ilaria Capo. She said that she doesn't exclude that the onset of COVID was caused by climate change. So it's just my opinion. I think it is unlikely. I don't think we can say that without global warming, with 1 degree less of global temperature, we wouldn't have got COVID-19. I don't think so, but this is my personal opinion. So take it as it is. Okay, now I think I got more or less at the stage where I wanted to get, because the remaining of this lecture is taken by this reference, is taken from this reference, which I suggest you to have a look at. It's free. And it's Climate Change for Health Professional, a pocket book. It is very practical. I mean, nothing very difficult. And the essence of this report is given by tables like this one. Sorry, I need to go back. Physiopathology of cardiovascular diseases in relation to climate risks. I think it is an interesting table because you see that it is focusing on cardiovascular diseases, but you find several tables like this in the following of the lecture and more in the pocket book. So, a table on cardiovascular diseases, it lists the main expression of climate change, the main event related to climate change, which are deemed to be related with this disease: heat, hurricanes, flooding, drought, air pollution, and cold. Actually, I have some doubts with the theory that tried to explain the cold waves as a consequence, as an effect of climate change. Actually, climate models don't really reproduce well these cases. So climate models predict a warming, but they don't predict an increase of the frequency of cold waves. Anyway, as you know, today any change in climate, we tend to attribute it to climate change and global warming, and so it's listed here. And for any particular manifestation and symptom which can be associated to cardiovascular diseases, this table presents the result from a literature review, which this review tries to identify the link. So, tachycardia after hurricanes, flooding, or drought, activation of the sympathetic nervous system due to stress and increased physical activity. Okay. Hypertension, acute and chronic stress, increased physical activity. Air pollution, no report in the scientific literature about links of hypertension with, or hypertension, depends on the pronunciation that you adopt, and air pollution. So I think that also these tables are very useful for you in order to understand these links. And as I said, same tables for respiratory diseases in relation to climate risks, neurological disorder in relation to climate risks, mental health disorder, skin diseases. And this is something that I leave to you for your information. If you're interested, these are easy to consult, and you have also the reference here. So we are getting to the end of our joint experience, and it has been a new experience for you and also a new experience for me. So anyway, I think it has been, for me at least, very interesting. Now, what is the advice at the end of the story? In the light of the several connections that we have identified, and first advice, the impact on the human health related to temperature and air pollution is relatively well understood. And while the dependence of other illnesses from extreme events is still the subject of ongoing research. And the impact of climate change on extreme events themselves is still poorly known. So the most important advice to give to patients and community is to get prepared and educated first on what is known about climate change in their region, what the impact on extreme events is expected to be, and to what extent the climate risks are relevant and increasing. And this is something I consider much important. Information avoid to undergo anxiety and therefore stressful situations. because I mean, I can really say that I see a lot of stress, a lot of pressure on people about the possible impact of climate change, and I would say too much. I think there should be instead more education, understanding. So to inform people is the first step. A useful advice, for instance, is to reduce the exposure of individuals and communities to the negative effect of climate. A useful advice is to inform people that the risk of getting the Lyme disease, the numbers are clear, is increased. So they have to get protected. So to give advice that helps to lower the stress and reduce vulnerability. And this is particularly important for the categories that are more exposed. So if you recognize that the elders are more exposed, these are the categories that you should inform. And this is particularly important in the regions where the healthcare system is weaker. And being informed, for instance, on the weather forecast and the reliability that we are expecting from the weather forecast is important. So people should know that the weather forecast is affected by uncertainty, but still very useful. So they shouldn't expect that the forecast is always correct. So I saw for the flood that we got in Tuscany, they issued an orange alert. And then it was a disaster, and people complained, and the institution complained because they said, why it was not a red alert? But I mean, when you get an orange alert, people should be informed that it may be red, and they should be prepared to react. And with maybe very simple things like bring the car one day earlier, because we get the forecast of the weather one day earlier. For the flood in the Romagna region, it was 2 days earlier. So take your car, bring the car in a safe place, so you don't have to be concerned about the car. Take your values into the house, put them at higher level, because it's clear that you may get a prediction, and a prediction of also the water level. And important thing, never consider that it's impossible to be flooded for you. I mean, in principle, every location can be flooded, every. And if you are close to a levee, the presence of a levee, people tend to say, I am safe because I am on the right part of the levee. But if there is a levee, it means that you are exposed, because there is a reason why people leave the levee. It means that there is exposure and the levee may fail. So it's important to deliver the information with a positive attitude. Keep positive when relating with your patients, because I mean, being very nervous doesn't help. Being anxiety doesn't help. Okay, so that's it. And as I said, let me stop the recording, and then I say final thing to you, which okay, here it is.